All right, welcome to The Explainer. Today, we are diving headfirst into one of the biggest, most mind-bending discoveries in all of science, quantum mechanics. It's basically the rule book for how the universe works at the tiniest, most fundamental levels. And as you're about to find out, things get really, really weird down there.
But look, don't just take my word for it. Richard Feynman, an absolute giant in physics, famously said that nobody really understands it. So, hey, the pressure's off. Think of this as an adventure we're on together, not to become experts, but to get a handle on why it's also so strange and just plain counterintuitive.
Okay, so to really get this, we've got to rewind the clock a bit, back to the late 19th century. At the time, physicists kind of thought they had it all figured out. You had Newton's laws, Maxwell's equations. It all painted this beautiful picture of a perfect, predictable, clockwork universe.
But there were these little nagging problems, right? These experimental results that just refused to play by the rules. They were like little cracks appearing in this perfect clockwork machine. For instance, hot things weren't glowing the way the theories said they should. Certain colors of light were doing weird things when they hit metal. And maybe the most alarming of all, the old rules basically predicted that every single atom in the universe should have collapsed on itself in a fraction of a second. So yeah, something was definitely deeply wrong. So who stepped up? Well, the first big ideas came from a couple of absolute giants. In 1900, Max Planck came up with this wild idea that maybe energy isn't a smooth, continuous flow. Maybe it comes in tiny little chunks, or packets, that he called quanta. He wasn't even sure he believed it himself, thought it was just a mathematical trick. But then, 5 years later, a young Albert Einstein took that idea and just ran with it. He said, what if light itself is made of these little energy particles? We call them photons now. All of a sudden, reality wasn't smooth anymore, it was grainy.
Now, those ideas were totally radical, but there is one single experiment. Man, it's the one that just lays the whole bizarre heart of quantum mechanics bare. It's called the double-slit experiment, and it gets right to the central mystery that physicists are still arguing about today.
Okay, step one. Let's imagine something super simple. We're firing tiny particles, think of them like microscopic bullets, at a wall that has two narrow slits in it. So what do you expect to see on the detector screen behind that wall? Well, exactly what you'd think, two stripes of hits right behind each slit. Simple, predictable, makes perfect sense.
Okay, now for step two. Forget the bullets, let's send waves through those same two slits. Think of water waves. As they pass through the slits, they spread out and start to interfere with each other. Where two wave crests meet, they make a bigger wave. But where a crest meets a trough, they cancel each other out completely. So on the back screen, you get this weird pattern of many stripes, places with lots of wave action and places with none at all. It's the only way you can answer the question, how can opening a second window actually make parts of a room darker? Wave interference.
All right, you ready? This is where reality starts to unravel a little bit. We're going to do the same experiment, but this time we'll fire electrons, which we've always thought of as incredibly tiny little particles. And here's the kicker. We're going to fire them one at a time. So there's absolutely no way they can bump into each other and interfere.
So what's it going to be? What pattern do you think they'll make? I mean, they're particles, right? So it should be the two bands, just like the bullets, shouldn't it?
Well, what happens is just impossible. Each electron shows up on the screen as a single tiny dot, a particle. But as you keep firing them, one after another, those individual dots slowly build up, and they form a wave interference pattern. It's as if, and I know this sounds crazy, each individual electron went through both slits at once, interfered with itself, and then picked a spot to land.
But wait, it gets even weirder. You're curious, right? You want to know which slit the electron actually went through, so you put a little detector by the slits to watch them. The second you do that, poof, the interference pattern just vanishes. The electrons start behaving like good little bullets again, and all you get are two simple bands. The very act of looking at it changes what happens.
So, yeah, that one experiment just blows up our whole common sense view of the universe. It forces us to throw out the old rule book and accept a new, deeply weird reality. So let's check out what these new rules look like. So, rule number 1, wave-particle duality. A physicist named Louis de Broglie had this brilliant idea. He figured, hey, if light waves can act like particles, maybe all particles, like our electrons, also have a wave nature to them. And he was totally right. That electron wasn't confused. It wasn't one or the other. It was both.
It was living this crazy double life, being a wave and a particle at the exact same time.
And that duality, that double life, leads to something else, a fundamental limit on what we can even know. It's called the Heisenberg uncertainty principle, and it basically says there's a cosmic trade-off. You can find out an electron's exact position, but if you do, you'll have no idea about its momentum. Or you can nail down its momentum, but then its position becomes a total blur. And get this isn't because our measuring tools aren't good enough. It's a baked-in feature of the universe.
So when you put all this together, you arrive at a really unsettling conclusion. The universe, at its very core, is playing the odds. That wave we talked about, it's literally a wave of probability. We can never, ever say for sure where an electron is going to land. All we can do is calculate the probability of it landing here or there. The universe, it turns out, doesn't deal in certainties. It only deals in chances.
Okay, I know what you might be thinking. This is all super weird, kind of philosophical, but what does it have to do with anything? Well, turns out everything. This quantum weirdness isn't just a curiosity. It's the engine that powers our entire modern world. No joke, it is the most successful theory in all of science.
Think about lasers, for instance. A laser works because we figured out how to get a whole bunch of electrons to make these precise quantum leaps, all at the same time, releasing photons that are perfect copies of each other. That creates the powerful focused beam that you see, and it's a purely quantum effect that runs everything from barcode scanners to the internet itself.
And how about that smartphone in your pocket? The transistor, the tiny little switch that's the building block of all modern electronics, it's a pure quantum device. The only reason your computer works is because we understand the quantum rules for how electrons move through silicon. Without quantum mechanics, there is no digital age. Period.
Ever had an MRI? Those incredible machines that can see inside your body without making a single cut? They're basically manipulating a quantum property of your atoms called spin. You can sort of imagine it like a tiny compass inside every atom. By watching how those compasses line up and flip, doctors can build incredibly detailed maps of your body.
And get this, even your GPS, the thing that gets you to your favorite coffee shop, relies on atomic clocks that are so mind-bogglingly precise they'd only lose a second over billions of years. And that precision comes from the totally predictable, quantized energy levels of electrons. It's just a brilliant example of how science's weirdest ideas end up becoming its most useful tools.
Okay, so let's boil this all down. What are the big takeaways here? First, at the bottom, reality is just fundamentally weird. It does not follow our common sense rules. Second, things can be both particles and waves at the same time. Third, the universe knows when you're looking at it, and it changes its behavior. And finally, and most importantly, all this weirdness isn't just an abstract theory. It's the engine driving almost all of our modern technology.
And that leaves us with one last, really deep question to chew on. If the electron only decides where it is when we look at it, what is it doing the rest of the time? What is reality when we're not looking? And that, right there, is the mystery that still sits at the absolute heart of quantum mechanics.